Thank you for joining us today. I'm Jo Hawkins. I work at the University of Western Australia in the Office of Industry and Commercial Development, and today we're hosting an industry briefing around quantum sensors. And it's all part of a bid for a new ARC Centre of Excellence in Quantum Innovation and Discovery Science. So we're calling it QUIDS, and you'll hear that acronym a bit today. And we're looking for industry partners to work with us, and we want to raise awareness of this really exciting bid and the capability we have here in Australia, in particular around sensing. The bid is led from Western Australia, but it is national. It's a truly national effort. And thank you again. And if you wouldn't mind, anyone who's in, if you can turn your video on, that would be much appreciated. Excellent. So we'd like to start with an acknowledgement of country. I'm here in beautiful Perth, Western Australia, and the traditional owners of the land on which I am right now are the Whadjuk people of the Noongar Nation. And we'd like to pay respects to elders past, present, and emerging. And in many Western traditions, time is seen as a straight line. It moves from the past to the present to the future. Of course, the Aboriginal concept of the dreaming has a concept of time where time is not linear at all. It's continuous. It's an ever-present reality. The past, the present, and the future are connected and happening all at once. And this is a very different way of thinking about the world and our relationship to the world. And it reminds me of quantum physics because I've been learning about both recently. And I think this is one of the most exciting things about this new technology. And of course, you know, a Western linear chronological understanding of time was only really brought into question by Einstein in 1905 with the theory of relativity. So, of course, quantum physics describes the behaviour of matter at the very smallest scale. So we talk about particles like electrons or a photon, which is a particle of light. And at this really tiny subatomic level, these particles don't follow the rules of classical physics that we were taught at school anymore. They can be in two places at once. That's something called superposition. They can suddenly appear or disappear, and they can become entangled. And what that means is if one particle spins, another distant partner can spin, even on the other side of the universe. And the team that's here today are learning how to harness these strange behaviours to create brand new technologies. And while some impacts are going to be felt far in the future, many of these technologies are being deployed into industry right now. And of course, our understanding of the quantum world, which is actually called the most successful scientific theory of all time, because it's been experiments have constantly proven it for 100 years. But our knowledge has resulted to lots of innovations already. MRI scanners and lasers, atomic clocks, that's all part of the first quantum revolution. But it's this phase where we can actually start to harness the actual qualities of quantum states to create things that we couldn't imagine before. So with that, now we've got a few people online with their cameras. I'm going to get Kate to take a quick team photo, if that's okay. Kate, she's going to count us in, and we'll just do that before we kick off. So can you count us in, Kate?
Okay, 3.
Okay.
3, 2, 1.
Awesome. Thanks so much. And just a reminder, you can place questions in the chat this whole time. Your videos are on, but your sound is not. So we'll communicate via the chat, but please, you can send us an email after this, and happy to talk to anybody. So I'd like to kick off by introducing Professor Mike Tobart. He's the director of the QUIDS bid and also the director of the Quantum Technologies and Dark Matter Research Lab here in UWA. He's undertaken groundbreaking research, including precise measurement instruments that have resulted in spin-outs. He holds multiple patents, but he's going to tell you more about that now and why he's really excited about this bid. So, Mike, I'll spin to you.
Thanks, Jo. Thanks for that. Yeah, I'm a professor at UWA. I run the Quantum Technologies and Dark Matter Labs here at UWA. These labs have been going for some 20, 30 years. At the moment, we're part of two ARC Centres of Excellence. One is Engineered Quantum Systems, and the other one is Dark Matter Particle Physics. They're funded by the ARC. These Centre of Excellences, they're bids that you go nationally with various labs to undertake some research with the common themes that couldn't be done otherwise by single institutions. That's the new bid that we're going through for. Engineered Quantum Systems is finishing, and I'm leading this QUIDS bid. So this has been led out, this new centre, which is a period of 7 years, will be led out of Western Australia. We have a lot of technology here that we have developed over the years, and there'll be a large node in Queensland. And I would like to point out that these are the 2 resource states. So it's exciting that we would be looking at the resource sector and translating technology. I'm proposed to be the director of this new centre, and the philosophy of the QUIDS Centre really follows closely what my research career has been about. At UWA, I have led this lab, and we do precision measurement and sensing. Our primary goal has been to do low energy tests of fundamental physics. And when we look for new signs of physics, we have to develop new sensing techniques, new measurement techniques. The sort of new physics that we look for is signs of quantum gravity, detecting dark matter. We have done the best tests of the constancy of the speed of light as predicted by Einstein, and we're looking for high frequency gravity waves. It's known that gravity waves exist at certain frequencies. You need these large interferometers, but we're building low temperature, high precision experiments on the tabletop that could look for megahertz gravity waves and above. And if they exist, it's signs of new physics. But when we build these new technologies to look for these really fundamental questions, we also we do jumps in technology by building new sensors that would not have been built otherwise. Because if we're doing an incremental sort of improvement of a sensor, you will never get orders of magnitude improvement. Throughout my career, we've developed new sensors that have done up to three orders of magnitude, a factor of 1,000 times better than was the day before we turned it on. So we're talking about huge jumps in technology that can lead to disruptive technology that will change the course of technology. So we have 13 patents. Besides the fact that we are searching for these fundamental questions, our technology in the lab, with great funding from the ARC and some other avenues, has enabled us to have this really great lab with as good as anywhere in the world, if not better. And we've been able to translate technology. One example was our gravity wave work led to a development of a technique that led to a factor of 1,000 better in noise performance of oscillators and clocks. And that led to a startup company which sold lots of technology for years until it was bought out by Raytheon. And every Raytheon defense radar has one of these systems that was developed in our lab in Western Australia. So this is a great culture, and we are looking to change the culture of research along the lines of my experience over the years, because in a lot of research labs, it's just fundamental research and a lot of ideas just dissipate and never get translated in Australia. So in a centre of excellence, you typically have the leaders of research who are doing the fundamental research, but you have many postdocs, students and people associated with that. For example, our group is about 20. Not all of those students will end up doing research as a career. The idea of this centre is also to change the culture. To change the culture of when we're developing our technologies, we look for translational outcomes. And this is really a continuation of EQUIS, which has developed this really nice way of doing this. And this sort of philosophy is undertaken in labs in the US all the time. I have good friends in the US, Jan Hoare and Gilla, who developed the the frequency comb and won the Nobel Prize. One of our postdocs went there and worked with him, developed a stable laser, and his name is Mark Knockcut, and he's now a president of a company called Stable Laser Systems, and they sell laser systems everywhere in the world. This is the sort of thing we can do in Australia, and this is what QUIDS will be about. That's all I will say, because the others will give more details. So thank you, Joe.
Thanks so much. And I'm now going to introduce Dr. Jeremy Borhill, who's an experimental physicist here at UWA. He's actively working right now to commercialise several innovations, including a breakthrough device with the potential to disrupt industries from medical manufacturing to telecommunications. So thanks, Jeremy.
Thanks very much, Joe. Going to talk to you a little bit about our thoughts and our what we imagine for this Centre of Excellence bid that we're calling Quantum Innovation and Discovery Science, QUIDS, which sort of has the unofficial motto that to see something no one's ever seen before, you must look in a way no one's ever looked before. And the idea is that we're going to develop new quantum sensing devices, as well as being the first customers of new commercial devices. So the high-level vision is that QUIDS will prototype and manufacture new quantum sensors and instruments that advance scientific knowledge, the kinds of big, hairy questions that Mike was talking about, while simultaneously delivering tangible value to Australian industry by de-risking quantum products and delivering immediate or near-term commercial benefits. And QUIDS will draw from about 30 years of experience in this field of quantum physics. Australia is actually a world leader in quantum physics research, and we punch well above our weight in academic metrics. But that hasn't really translated into the kinds of technology and commercial benefits that we see in the US and in the UK even. It's something that for whatever reason, cultural or geographical, Australia could really be improving on. And both federal and state governments have been investing in this area for decades, with over $1 billion invested. And it's resulted in a wealth of IP and infrastructure and innovative thinkers sitting in Australia's universities, which means that there's an existing R&D pipeline that's primed to be capitalised on right now. So the ARC Centre of Excellence, as Mike said, it's a national collaboration. You can see at the bottom of the page here, there's 6 institutions that are proposed to be in the QUIDS bid. We have a bunch of professional and academic staff across these institutions, each of which have about 20 or so early career researchers and PhD students underneath them. There's also international collaborations, as you can see in the bottom right-hand corner, Jefferson Labs, Fermilab, NIST, CERN, who will be collaborating on the design of new tech sensors, quantum sensors, and the discovery science that we want to do. So why quantum sensing? You might be wondering what these devices can deliver. Well, as Mike mentioned, that they can produce orders of magnitude, thousands of times improvements over their classical incumbents, which fundamentally allows us to expand the bounds of what can be sensed. And this sort of has 2 main advantages. One is that we will have more robust and higher resolution sensing for existing and new industries. But this will also allow us to try and discover new scientific breakthroughs by detecting the undetectable, which has potentially unforeseen implications for the commercial sector. So what's a quantum sensor? You may have heard of the term qubit. Well, qubit is the quantum version of a bit. And a bit of information is something we talk about in classical computing that you can generate with a transistor. And a transistor can be in either a 0 or 1 state. That's our binary language, right? And this 0 or 1 state is called a bit. Now, because of the weird and wonderful properties of quantum mechanics, qubits, the quantum versions, which can be an atom or an electron or a photon, can exist as both 0 and 1 at the same time. So I represent this as a spinning coin, as opposed to the transistor that can only be heads or tails. the qubit is spinning. So it's both 0 and 1 at the same time. And this gives qubits an exponential computational advantage. So you've probably all heard about quantum computing. The federal government has just invested about $1 billion into a quantum computing startup, PsiQuantum, who I'm sure you've all heard about. And it sort of demonstrates how serious we are about this technology. But one of the biggest challenges with quantum computing is that it's very, very easy to stop this coin from spinning. And this is because qubits are extremely sensitive to small signals in the environment. Now, this is a huge challenge for quantum computing, but it makes these devices actually fantastic sensors. And so while quantum computing might be around 10, 15, 20 years off, quantum sensors and quantum sensing technology is here right now. So the types of sensors and the types of things you can sense with these devices is across many, many different physical platforms. We have time, magnetic fields, rotation, gravity, light, and these are non-exhaustive. There's other things you can try and sense with these devices. And like I said, the quantum version of these sensors will offer orders of magnitude improvement. But additionally, because of their fundamental nature, they are calibrated to fundamental constants. So the speed of light, for example, which means that your calibration of your sensor doesn't degrade over time. The speed of light has been what it is for about 13.7 billion years, and it will continue to be so. So there's as well as the improvement in sensitivity, you also have the improvement in robustness of these devices due to that fundamental nature of how they work. Here are some of the technology readiness levels of some of the use cases of atomic clocks and magnetometers, for example. And you can see that while some of these use cases are early days, some are well and truly being utilized right now and are ready to be commercialized. So for the resource and energy sector, we can improve the detection and extraction of natural resources using detection of gravity. You can put a quantum sensor down a drop hole that's going to physically feel a different gravitational pull depending on if there's a large deposit of ore underground. And we'll be able to do so with much higher precision and much greater robustness than classical incumbents. For defense and security, position, navigation, and timing, things like gyroscopes and gravimeters that will be limited to the quantum level and quantum precision will be really, really valuable for GPS denied navigation, which is, I think it was modeled recently that GPS being down for a day is a multi-billion-dollar problem for the world and for defense. All of our defense forces navigate using GPS. So if that system were to go down, we need a backup. And quantum sensors are primed to be an excellent solution for this. As well as healthcare and medical imaging, we can improve our resolution without needing to step up the power of what you're using to detect, which is really, really important with biological systems, because when you step up the power too much, you typically tend to burn the thing you're looking at. So quantum sensors offer an alternative route to better medical imaging. So the structure that we envisage for QUIDS looks something like this, where we have our two research verticals, which we are calling quantum foundations and beyond standard model physics. And they have these two cross beams of culture and innovation and quantum sensors and networks. And this is the first drive of the center. So the two verticals, quantum foundations, is really about the fabric of reality. So as Joe mentioned in her introduction, quantum physics is the most successful scientific theory we have. It is excellent at predicting the world that we observe and experiment. But it's a mathematical model, and it's still up for debate, and it's not settled what that mathematical model actually really means. When we talk about the wave function, we're talking about equations that can be written down and accurately predict what we observe. But what the wave function really is in reality, and whether or not we are really transmitting information faster than the speed of light with entanglement, these are all questions that are still up for debate. So quantum foundations looks to try and answer some of those really fundamental questions about the universe. Beyond standard model physics goes to some of the grand challenges that still face physics, like why do gravity and quantum mechanics not marry up? What is dark matter? which is about 80% of the mass in the universe. We have no idea what it is. These are questions that need new technology to try and answer. And as has been mentioned, to try and answer any of these questions, we're going to need to look in a new way. So we're going to need to develop new technology. So that's why these two verticals are linked through the quantum sensors and networks crossbeam, which will be the research and development going into building these new devices and testing these new devices, as well as linking them up. So the network portion here is that we can gain an advantage, a competitive advantage from these sensors by having multiple of them and varied kinds of them all synchronized up together across the country and potentially across the world, as well as culture and innovation. As Mike mentioned, a large legacy piece of the centre is to change the culture in Australian research to being one that focuses on real world impact and translation. And we believe that this starts in the education sector, as well as community engagement, as well as the culture within academia itself. So the work and the IP that's being generated out of this first drive, we need an infrastructure around coming into the centre, realizing what has commercial appeal and commercial potential, and translating it, which is where the second drive of the centre comes in, is to have infrastructure and staff who are going to take that IP, that valuable IP, and say, hey, you know who really needs that? The pharmaceutical industry or the resource sector. They're dying out for a solution of this kind that you've developed to try and detect dark matter. Well, we can use it here. And then to take that technology and push it all the way up to the edge of commercialization, which is what the ARC can fund. And then through a third party, look to advance that mid to late translational readiness level product into a mass marketable product, which will then feed back into the science. Because like I've mentioned, QUIDS will be the first customer for a lot of these technologies, which is a really, really valuable role that it can play in this ecosystem. Is to take these products at their TRL 8 or 7 level and be like, well, let's test them in the environment, let's test them in the lab, because we want these devices to be able to run some of our experiments. So speaking of that research and development pipeline, this is sort of another perspective on it, that we have a strategic R&D plan where those two drives will feed into this third party deep tech venture studio, which will really focus on the pre-seed and seed stage, and building teams around the IP that's being generated out of the translation program. That translation program, that Drive 2 research translation program, essentially what it offers is researchers within the centre both funding for infrastructure that they might need to pursue the translation of their technology, but it also will fund their salaries to provide them time to really pursue these translation opportunities, which is something that is built off an existing program in EQUIS, the Engineered Quantum Systems Centre of Excellence that Mike mentioned, and was extremely successful. And that translation program in EQUIS had about a 3.5-year runway. So we're really excited about what it could do with a 7-year runway starting from the very beginning of QUIDS. So in just 3 years, that EQUIS program had about 200 participating researchers, funded about 48 projects to the tune of about 200 to 500,000 per project. It resulted in 12 startups with 5 to 8 more potential startups still to come, 5 licenses and 1 exit worth about 40 million. All in all, it had about a 40-to-1 ROI, return on investment, which is fantastic, and really demonstrates the value of coming into the research sector and saying, hey, you've actually got some valuable IP that with a little bit of care and love and attention, and if we can fund you and afford you the time to give it that care, love and attention, can really become something valuable. And all of this will be partnering and almost taking on the baton that Quantum Australia, the work that they've done, which is a new national centre for quantum growth, which the whole purpose of Quantum Australia is to prime industry for quantum technologies, which at the moment has about a 1-year overlap with QUIDS, finishing in 2027. QUIDS proposed to start in 2026, which feels really like perfect timing to take advantage of and capitalize on the work that's been going on in this sector. So one of the roles that the translation and the commercialization branches of the centre will need to do is to take these quantum technologies and make them robust and durable. There are some classical engineering challenges around quantum sensors that need to be worked on. So while these things are extremely sensitive to the type of phenomenon you're trying to detect, whether it's gravity or acceleration or rotation or magnetic field, they're also very sensitive to a lot of other environmental influences. So work needs to go into sensor stability, materials engineering and purification, as well as device engineering itself and scalability. And these are the sorts of activities that will go on in the translation arm, as well as the commercialization arm of the centre, which will really focus on maintaining that competitive advantage you get from being a quantum sensor, the performance, whilst optimizing size, weight, power, and cost. So we'll really focus on bringing quantum out of the lab and into the real world. And with that, I'm going to hand over to Joe, who's going to talk to you about where industry can play a role in the quantum center.
Joe, muted.
There we go. Thanks, Jeremy. And you know, Jeremy's really highlighted the importance of industry partnership, and our partners are going to be absolutely central to everything we do. And you know, there's lots of benefits from partnering with us, and there's going to be lots of opportunities to partner, right? So as far as official partner organisations, you know, the numbers for that will be, there's a limited number of partners we can take on. However, we're going to be building an on-ramp into the quantum ecosystem and a community around this space. So there will be a space for everybody. And I forgot to mention before, but I do not have a PhD in physics. I'm a non-physicist. I am, you know, really enjoying learning what learning from the team. But we talk a lot about quantum awareness in the lab and how much you need to know to make a good decision. And I think that's somewhere we can really add a lot of value. There are no silly questions here or in our physics labs. Indeed, quantum physics was founded by people who had the audacity to ask silly questions. So it's a safe space. And with that, I'd also encourage you to place your questions in the chat, because we'll be getting to those in about 10 minutes. So yeah, benefits of being a partner organisation are many, and it's going to, you know, we'll work with you depending on your strategic goals. Of course, the competitive advantage associated with being an early adopter is not just limited to visibility of the latest innovations and the ability to benefit directly in the near term, but it's also knowing what's coming down the line, being able to access talent, upskilling staff and senior decision makers. There is opportunities to inform and influence the research agenda. We really welcome those insight-led contributions to strategy, and you'll be part of a global network. And actually, what I really love about this is our industry partners will be able to access infrastructure and facilities locally and capability locally. So it's, yes, you'll be collaborating nationally and internationally, but ultimately every node that we have has infrastructure and people there in your local place. So you can come down to the labs, you can get to know everybody, and it's all about building that community. So, you know, would your organisation be a good fit for QUIDS? We want to truly work with organisations where we can add value and there's good strategic alignment, and you can always drop us a line after this and we can talk that through. Contributions can be in kind or cash. In-kind contributions are extremely important, and we can talk about that. That can look, you know, access to subject matter experts within an organisation, senior decision makers, C-suite, really understanding how technology is adopted, access to vendors that we can work with to commercialise, because I think often we'll be commercialising in collaboration with existing companies. It's all on the table. So if you did want to partner with us, what it would look like is reaching out, we'd meet, discuss your strategic goals, priority areas, delve into use cases, and then probably end up drafting some kind of MOU outlining that and mechanisms that might create value within your organisation. And again, that could span from having a PhD candidate or a researcher in your organisation working on a project, or you can put cash towards challenges that then attract the interest of researchers. And there will be, you know, this is a big centre that we're proposing. So, and then that would attract researchers to work on a specific use case for your organisation. Again, there's just a multitude, so I won't go too much into them now. But I will talk briefly about IP. We have a commitment to ensuring clean and clear ownership of IP. That is a fundamental principle of QUIDS. Our aim is to get that IP out of the lab. And we've got a strong track record in reaching commercial terms. And I was thinking about our competitive advantage and why we're so good at this. And I think it's really simple. It's just communication and managing expectations, because to get IP out of the lab and into the world, it's a collaborative effort. And you're working with the researchers, industry, and also the university tech transfer officers. Because what happens generally with centres like this is the ownership and rights of the IP generated vests within the research institutions, right? So it vests within the universities. That's really standard. We work with that all the time. And in fact, generally, our industry partners are not interested in kind of owning IP specifically, just for the sake of it. They want a solution to their problem. So we operate quite holistically. We are super flexible as well. I must say that this is generally, I'm outlining generally how it happens, but we are very flexible, and it depends. Is always, you know, the terrible answer to give, but it's true. But yeah, generally, industry partners prefer, rather than owning IP, they want, yeah, solution to the problem and a vendor to provide it, right? So this is why venture creation is key to this. Although QUIDS will also be, I'm sure, working with industry inside their own R&D departments. That is also absolutely something that could happen. And the reason that you might not want to own IP and instead you would have a first right of refusal is that it just allows you to evaluate IP before it's offered to anybody, before anybody else has seen it, without contributing any significant resources up front. And then you can choose to invest in whatever technology aligns with your own business, and then you don't have to be burdened by an IP portfolio and managing and protecting that. We would do all of that. And I won't say any more for that, but if there's any other, and there's always so many questions about IP, you can always contact me directly and we can talk you through. And I guess with that, I think that's the end of my section. And then Kate is going to bring us home to question time by talking a little bit more about ARC Centres of Excellence and what they actually are.
Thanks so much, Jo. So just for those who perhaps haven't worked a lot with universities before, I just wanted to remind everyone what the Australian Research Council is, because you may have heard us use the acronym ARC a few times. So that's the Australian government entity that is the primary funder of grants for research. So they're really focused on supporting the highest quality fundamental and applied research and research training. So Centres of Excellence are the flagship opportunity of the Australian Research Council. It's only offered every 3 years. It's worth $35 million over the 7 years. So this is a really significant investment from the government. And it's part of the linkage program, which is the key research funding stream, which supports collaborations between academia and industry. So Jo mentioned that the opportunity to partner in a centre of excellence, is something special and rare. This is obviously, taxpayer funded. So the type of partner that we're looking for is partners that do have that long-term view, who really are committed to working with the sector to produce something that is of value to industry and society. Obviously, the government, in funding these kinds of initiatives, is interested in the commercial outcomes of economic growth and jobs and economic benefit for the organisations that partner. But there also does need to be that big picture, long-term view to really get the most out of a collaboration of this scale. So just to focus on what needs to happen, because it is a two-stage process. We're about to start the EOI stage. So we're anticipating that will open mid-August, and it will need to be submitted at this stage. The date that we've been given is the 18th of September. And at EOI stage, we don't need specific budget detail, but we do encourage you to start talking with us now so that we can start that negotiation process, because it's really important that we create a shared understanding of how your organisation wishes to contribute to, but also benefit from the research, because that forms part of the narrative of the EOI submission. And there's two ways that you can participate. You can simply be a partner organisation, but partner organisations can also choose to nominate a partner investigator. And that partner investigator would normally be someone who has scientific expertise and that can dedicate their time to the research program. So they actually become an active researcher alongside the researchers that are based within the universities. At full application stage, we do ask organisations to provide a formal letter of support that would detail the in-kind or cash contribution. So just to show you the timeline, so there's a lot of work that has been leading up to this point, and the researchers are getting together next week to have another deep dive. But we're really opening up the conversation to industry, to hear from you about what you're looking for and how we can work together. The EOI, as I mentioned, will be opening mid-August and submitting on the 18th of September. Then the full application stage will be from January to March 2025. The successful bids will be known in November 2025. And then if we're successful, the Centre of Excellence would operate from 2026 to 2032. So that's a 7-year runway. So this is a really exciting opportunity. We do hope that you'll ask us lots of questions and make an appointment to discuss further. Obviously, we have the team based here in Western Australia, but it is a national centre. So depending on where you're based, we may put you in touch with the researchers that are closest to you. It is a really deep collaboration and we look forward to having you on board. Thank you.
Fantastic. Thank you so much for attending today. And now we would love to answer any burning questions. I know sometimes with topics like this, it is, there are so many questions. Now I can see there are no questions at the moment in the Q&A or the chat, but you've got us all here. So something else we could do if you prefer is, I've got a question here in the chat from Liz. So yeah, that might be one for Kate actually. And Liz asks, is it just letters of support at this stage for the expressions of interest? So no contracts at the application stage? When does the actual contracting and negotiation happen?
So the contracts would be drawn up when the final funding decision is made. And there is a standard template for Centre of Excellence or Australian Research Council agreements that's available on the Australian Research Council website, but we'd be happy to obviously to find that link and share it with any industry partners that did want to see those principles. And there's a few other key documents that may be useful on the Australian Research Council website, such as the National Principles for Intellectual Property for these commercially funded grants, which is a really good reference document for how intellectual property is treated across the sector. But just to be clear, at EOI stage, what we need is permission to name the organisation. So there isn't a formal letter of support. There doesn't need to be specific dollar amounts committed, but we do need to have a shared understanding of how an organisation or a partner investigator would be contributing to the work. And then at full application stage is when we need a formal letter of support and the formal budget will be drawn up.
Thank you, Kate. I can see Sean has a question here about, is there interest in a commercial fabrication capability? Now, I've got some thoughts on this, but I think Jeremy's probably best placed to answer. What do you think, Jeremy? Should we make this a team effort? I will say before Jeremy takes over that that all of the universities involved, we're so lucky to be able to benefit from NCRIS, which is a national collaborative research infrastructure program in Australia, and we have fabrication facilities as part of that. But yeah, absolutely building out advanced manufacturing in Western Australia and Queensland and New South Wales, Victoria. There are state plans to do that, and we would be working very closely with state governments. I think we should be really ambitious. So Jeremy, I might go to you.
Yeah, I can just add briefly to that one of our partner organisations that we've lined up already is Australian Nanofabrication Facility, ANFF, who have nodes all over the country, and essentially will be offering the centre access to their fabrication facilities, which will be really, really important for that translation step for taking your design into ANFF, developing a recipe essentially that can then be scaled up and taken to any foundry anywhere in the world, and they can mass produce your little widget for you. So the discussions of ANFF have been really, really positive, and where we're looking forward to working closely with them. Yeah, Marius is a key member of the WA node here. Yeah.
And I mean, the great thing since the publication of the Australian quantum strategy last year, the efforts, I think, to really for the states to work together on that national vision, you really started to see that coming to fruition. And I think and we work nationally and globally a lot, and what we talk about is for each region to thrive and I guess lean into their competitive advantage and their talent and their infrastructure in a specific way as part of that national story. And I think that's fundamental to QUIDS. Okay, we've got another question here from Bill. Besides money, what's your biggest need, hardest problem to solve? Okay, I've got this immediately. I know exactly what I'm going to say to you, Bill, and that is building teams around this tech, right? We have more talent and capability and, let's face it, IP than we probably know what to do with. There was when we talk about, EQUIS has been named a few times. EQUIS, even I trip up on all the acronyms. The Centre of Excellence in Engineered Quantum Systems. So we've been involved. UWA has been involved in that national centre, headquartered in Queensland, and the success of EQUIS has been absolutely extraordinary. I think there is a built-up kind of there's tech that's been built up within the labs that we can commercialise. So yes, commercial capability, entrepreneurs, people that want to get involved, industry that want to get involved and co-create with us, get this IP out of the labs and into the world and growing the Australian economy. I was just reading something today. I think I wrote it down. It was Tim Ayres. He did a speech recently. He's the Assistant Minister for Trade and Manufacturing, and he was talking about opportunities for Australian re-industrialisation. And he said, this is a train that only leaves the station once. And he was talking about a few different advanced manufacturing opportunities, but he was talking about quantum too. So this is the time. Okay, we've got Liz again talking about the Venture Studio and how does that fit into the Centre of Excellence exactly. Now, Jeremy, you spoke a little bit to that venture studio. Would you mind talking a little bit more about the difference between, I guess, a founder-led approach and an IP-led approach?
Yeah, I can do my best. My understanding of the need for a venture studio is that the venture studio will exist outside of QUIDS, and will be will almost be a third party, but be very, very closely related, because ARC funding cannot be used on commercialization. It can be used on translation, which can take technology right up to the point of commercialization. But when you start wanting to market your technology and spin out, and the cost associated with the engineering, as well as the research and the marketing around those, that must come from another source, which is why we need to have this third party. That's because it's sort of where the gap is right now in technology coming out of universities. There needs to be something like a venture studio that can take this technology the way to being marketable and being ready for market. So that organization will look to have the infrastructure that will build the kinds of teams Joe was talking about around researchers, and help them get their technology to market and get to those high TRL scales. In regards to founder-led versus venture model, Joe, you may need to take over there.
Yeah, I think it was more, thinking about the general, for the last probably decade or so, an accelerator program model has been most popular, which and they're really good. Like, we've had great experiences with researchers going through accelerators like CSIRO on Prime, and if you don't know about that, you should, because it's an amazing program where the researcher is founder, and the researcher will go out and end up being the CEO or the chief scientific officer of a company, and that does happen. But we also want to have opportunities for entrepreneurs to come in and help steward and help build these new businesses, and that's exactly what a venture studio does. There's also a question I can see around culture change. And again, it's interesting, all these questions kind of, are very thematically similar. And it's a question from, Jordan, saying, can you please elaborate on the culture change aspect of QUIDS? I might give that to Jeremy and Mike.
Yeah, I can say something about that. So I can say that from my experience in the past, we started a startup company that translated our technology. But the reason we could do that is because we had one hero. His name was Jesse Searles. He was actually from the US, and his father that's what he did as a job. He translated technology from universities in the US, and he brought that culture to our lab in the 90s. If it wasn't for him, it would have never happened, because in our lab, we didn't have the culture of translating research. We had to have someone from the US with that culture who was working on the project, which was extremely lucky to enable this to happen. And he took the risk. He was the risk taker, and his father backed him. So you have to have the risk taker. So this sort of culture of taking risks and translating technology has not existed in Australia. It is starting to exist now, and for example, in the US, where a similar company called OE Waves started in California, and that had a lot of backing from the government through programs of translation technology. So in Australia, you can't just do it like that. But I believe I've seen over my time, gradually, the younger people coming through, more eager to take these translational risks and try and make a company and try and make a name for themselves this way. And this has started through the prior Centre of Excellence, Engineered Quantum Systems, who's brought in this translational program in the centres. This can only be done on a 7-year scale. It cannot be done in the normal funding cycles. You have to have a special program which is on the order of a centre to enable this to happen. Because you need the network across Australia and the body of researchers and students and that who will take interest. And I am seeing this culture change at the moment, and QUIDS will help facilitate and fast track this culture. So I'm very excited about that. I'm very excited about seeing a lot of opportunity go away in the past. A lot of opportunity in the past was not taken up. Now we'll, as a nation, we in the future we'll be able to take that opportunity. And I think it's very important if we want to become like Europe and the US and translate lots of high-tech technology and not just do primary industry. I think this is highly important. I don't know if anyone else has got anything to say.
Yeah, I might just add to that. That like Mike said, you know, getting research out of the lab is part of culture, right? And it's a culture that exists in the US, but the landscape is slightly different in Australia. So I think it's really crucial for QUIDS to be changing this culture. We need to have strong industry alignment. We need to make sure that what the researchers are trying to commercialize, there's a demand locally for that. So that's why we're really keen to partner with industry organizations from the very beginning of this center, so that we're both on the same foot together and looking at what is needed in this country and what sovereign capabilities we can develop here by being partners from day one. But the other piece of the culture and innovation of the center really looks at the inlet valve to the research sector, which is education. And diversity of participants in the research sector. If we want to have a really flourishing industry, a quantum ecosystem here, it needs to be diverse and it needs to have people. And what we're seeing in secondary schools is physics participation rates plummeting. And I believe it was recently modeled that if it continues at the rate it's going at, in 30 years, we'll have no physics undergraduate researchers of any gender or any diversity. So it's a big problem that Australia is facing is how can we change the culture around physics as a research subject so that people of all walks of life want to participate in it, but then also once you're participating in it, can you get real world impact out of what you're doing? So there's definitely sort of the way I see it is that there's two elements to the culture and innovation sector of what the centre wants to do, and that's the inlet and the outlet of the centre.
Thanks, Jeremy. And yeah, diversity, we haven't talked a lot about diversity and innovation in this session, but it is absolutely, it's been core to, you know, a lot of Mike and Jeremy and Jacinda, and we've got lots of you know, leaders in that space, and it is absolutely key. And I think for me, what I've enjoyed most about working with Mike and Jeremy and Jacinda is that truly, I think these labs in physics, they are, you know, creating cultures where they create space for new and diverse talent, and people will move aside and create opportunities and really listen. So that's fantastic. And I like Liz, make physics great again. Thanks, Liz. Great comment. I wanted to just read out Sean's comment, and Sean would love to get in touch after this because I think infrastructure is really important. So Sean made the comment that ANFF is still very research orientated. A commercial foundry capability is still a gap in local capability. We're looking to provide some capability in this space, but dependent on a local demand signal. So certainly let's chat. That sounds fantastic. There's also two great questions from Isaac. The first one, have you encountered any unique IP challenges and barriers associated with quantum tech? And then secondly, another big one, what do you view as Australia's role in the global quantum ecosystem? Does anybody, I do have, what do you think? Jeremy, do you want to take the first one? Or would you like me to have a
yeah, look, the only thing I'll say is that there is some sensitivity around quantum technologies, obviously from a defence point of view. which is something that must be taken into consideration and will be seriously considered by QUIDS and the plans we have around it. The advantage we have as a country, Australia, is that we're a part of AUKUS, and quantum technologies and quantum sensing is a key pillar of AUKUS, which means that there is relatively free sharing of information and low risk between collaborating with researchers in the UK and the US. But certainly from a critical technologies point of view, there are associated risks with the IP there, which is just something that I've come across, and consideration needs to be taken about strategically publishing and strategically collaborating around the work you're doing. I don't know, Joe, if you had anything else.
No, that was great. That was a great answer, I think. I think other than that, it is quite similar to any other kind of deep tech innovation. But yeah, AUKUS, I think that potential of AUKUS is we're only just beginning to see what that's going to do for us. I think that has got the potential to crack open the whole market. And what do you view as Australia's role in the global quantum ecosystem moving forward? Well, for me, I mean, I think there's a lot of very ambitious people across Australia who believe that Australia needs to defend and maintain our position as top of the pack. We've been leading for 30 years, and we made very early, very clever investments in quantum, and we've built up this incredible talent base, right? But over the last, few years, other nations are trying to catch up, and they're making massive investments. And look, they're attracting a lot of our best and brightest, right? There's great opportunities in other nations, but ultimately quantum is, and again, we haven't talked a lot about this, but it is a vital part of Australia's sovereign capability. We need this expertise here. We need, and it's just going to be huge business, huge for productivity and huge for startups.
Yeah, I can add to that.
Yeah, great.
Say in the US, the Department of Energy in the US started 5 quantum centers, run out of their government-funded research labs. I was on the midterm review, and I've also been on their quantum roadmap team, road mapping the next X years of quantum technologies. So yeah, there's a big push, especially in the US, on quantum technologies, but we have a lot of partners in the US. So there's a synergy there, and the same in Europe. There's a big push in the UK and others. But specifically, we have a good relationship with the US, and we're doing a lot of projects. That's for my research, particularly. So yeah, there is a big push, and the one thing for sure, they've got 5 centers in the US. I don't know, Australia has a couple, and they also got this new Quantize program where the DOE is funding special projects in quantum technologies, and I'm actually part of a few bids in the US going forward right now, and they're due soon. So really, we can't afford not to have quantum centers, to keep funding quantum centers. Otherwise, we will lose our advantage. And this is one of the ideas of QUIDS, and why I'm pushing it as director. One, I think it's great to lead it out of Western Australia, which is a huge resource state, but with the rest of the nation. And 2, we have strong contacts with the US. We can keep up with the other countries. If we don't fund these quantum centers, we'll no doubt lag behind, I believe. I think that's what I've got to say.
Thank you, Mike. And thank you so much, everybody, for attending and asking such great questions. And we'll be in touch after this. I'll send you all an email. And of course, you can always book in a chat with us if you've got other questions. It's a big topic and it's a big opportunity. And we're really excited to be able to kind of build this with you. So with that, thank you so much. And hopefully we'll speak soon.